right, so what if our x variable is also continuous? What if x is also continuous? Then our CDF of x, or our marginal CDF of x, remember this thing is just defined to be the probability that x is less or equal to x, just remind you of that. This thing is, it's really just the integral from negative infinity up to x of the density function for x, evaluated at some mark, let's say t, right? It's just the just this whole thing, right? It's just the area under the density function. This is f sub x, right? It's just this integral. It's the chance that this random variable takes on a value less than or equal to little x. Now this, though, I know now that I can write that integrand as another integral, right? That is, f sub x of t I can write as the integral over all the reals of the joint density function for x and y at t and y. Okay? Where I'm integrating here with respect to y. Dt. Sorry. Yeah, so just to make this clear, this is this stuff right there. Okay? So now, by interchanging the integral signs, swapping the order of integration, I can write this as the integral over the reals, and then the integral from negative infinity up to x of f sub x and y, t and y, dt, dy. Okay, why did I write it like that? Well, let's see. So just keep that in mind, and think this way. This is also true, right? We can also reason this way. The CDF of x, again, and I'll just remind you that this thing is defined to be the chance that x is less or equal to x. I'm going to stop doing that soon. This is the integral over the reals of the probability. Let's see, I'm just going to condition on the value of y here. It's the probability that x is less or equal to little x given y equals y times the density function for y, dy. Okay, and so this is just the law of total probability. Right? I'm conditioning on the value of y. So it's just, you could think of this as in the discrete case, remember this would be like a summation sign, and I want the chance of this given that times the probability of that effectively. Remember this stuff over here, this f sub y of y dy is like the probability that y takes on a value between little y and y plus dy. Okay? All right. So then, so what is this? This is the integral over the reals of the conditional CDF of x given y, right? Times f sub y of y, dy. Okay. Now I want to compare this to this expression that we got up here. They have to be the same thing because they're both the expressions for the marginal. I'm sorry, they're both expressions for the marginal CDF of x. So this suggests that this integrand maybe ought to be same as this integral, right? See that? So let's write that down. This suggests you can set this conditional CDF of x given y times the density function for y equal to the integral from negative infinity up to x of the joint density function for x and y, like so, right? Or that if I just do like this, a conditional CDF, that is this is the probability that x takes on a value less than or less than or equal to little x, given that y equals y. This can be written as the integral from negative infinity up to x of f sub x and y, the joint density function for x and y, divided by f sub y of y, okay, dt. All I've done is just divided both sides through by this f sub y of y function, okay? And so what is this? This is what we're after here. This is what we'll call this integrand here. We call the conditional density of x given y. Okay. Good. Notice that it is, in fact, it's a function of x and y, or in this case, t and y. Okay, it doesn't matter what you call the variables, but these are right. It's the idea is this is maybe we could write it like this: f sub x given y of x given y is defined to be that stuff. Okay. It sort of mimics the way we define conditional probabilities, and also the way we define how we define conditional CDFs. Okay, so it's kind of nice that it takes on that form, and that's what it is. If we set y and then integrate the other variable out from negative infinity up to some mark, that gives us the probability. This whole thing, what this is the probability that x is less or equal to x given y equals little y. Okay?